In this talk, we will propose a compile time identification of the impulsive variables at mode change events in Modelica. This is joint work with Benoît Caillaud and Mathias Malandain. In release 3.3 of Modelica and after, state machines with different DAE dynamics in each different state were added. This was an important step toward supporting multimode models. In papers 1 and 2 of this session, we propose the compile time structural analysis at all modes and mode changes. Impulsive behaviors can exist at mode changes. They lead to difficulties when generating simulation code and performing runtime executions. In this paper, we address the following two questions. First, can we identify impulsive behaviors at compile time? Second, can we take advantage of this when generating simulation code? We show in this picture two examples of systems exhibiting impulsive behaviors. On the top, we show an idealized planar cup and ball game. It's formalized as a variation of the celebrated planar pendulum when the rod is replaced by a rope. The tension of the rope is impulsive at the event when the rope gets straight. On the bottom, we show a simple idealized clutch. The torques get impulsive at the event when the clutch is engaged. In the paper, we develop the cup and ball example. In this talk, we develop only the simpler clutch example. We begin by recalling the essentials of structural analysis at mode changes for the clutch. Then, we proceed to the impulse analysis. We indicate how the impulse analysis can be made systematic. And then we conclude. This is a model of the simple clutch. Each shaft has its own ODE dynamics. If the clutch is engaged, which is captured by the if branch, velocities are equal and torques sum up to 0. Due to the constraint on velocities, the resulting model is a DAE of index 1. If the clutch is released, captured by the else branch, torques are 0 and the two shafts don't interact. The resulting model is an ODE. We explain our impulse analysis on this example and we begin by recalling the structural analysis. To prepare for the structural analysis at mode changes, we first discretize the clutch model with fixed time step epsilon and use a forward Euler scheme for the derivatives. Here, x bullet denotes the forward shifted version of x, meaning that x bullet of t equals x of t plus epsilon. In the following models, it is understood that x dot expands in this way. To avoid the approximation errors when using a fixed time step discretization, we use an infinitesimal value for the time step epsilon, meaning that epsilon is smaller than any positive non-zero real number. Since our structural analysis must be really multimode, we first add the needed latent equation for each mode. The latent equation is shown in red for the engaged mode, and there is no latent equation for the released mode. To prepare once more for the structural analysis at mode changes, we take two different forms for the latent equations. Within DAE modes, we differentiate the constraint omega1 equal omega2, and at mode change released to engaged, we shift it forward. Since x dot and x bullet are related via the Euler scheme, the two ways of generating latent equation are equally correct in that both determine the leading variables. This is the model we use at mode change release to engaged. It consists in chaining the two successive instants. In blue, we show the last instant of released mode. It is followed by the first instant of engaged mode in black. Bullet tau, also called previous tau, denote the torques at previous instant, and the same holds for velocities and their derivatives. Note that previous omega prime expands as 1 over epsilon omega minus previous omega. It therefore involves omega. A conflicting subsystem results pointed by the big stars colored in red. This conflicting subsystem has three equations, but only two dependent variables, omega-1 and omega-2. This is a conflict caused by the consistency equation of the engaged mode. We regard it as fake. Erasing the fake conflicting equation E3 removes the conflict, so E3 no longer holds at mode change. By doing so, we just delay the satisfaction of E3 by one non-standard instant, since it will be satisfied at the next instant and after. This is harmless, since one non-standard instant takes 0 physical time. So, we end up with the blue subsystem shown. It collects the equations determining the dependent variable at mode change, namely the next values of velocities, next omega, and the two torques, tau. Recall that derivative expand using Euler's scheme. We are going to use this model for our impulse analysis. We now move to the impulse analysis. We recall here the model we use for our impulse analysis. It determines the next omegas and the taus. The values for the next velocities are the restart values for the engaged mode. We show again the same model by expanding the derivatives with explicit first-order Euler scheme, having time step epsilon. Recall that epsilon is infinitesimal. Since epsilon is infinitesimal, the first idea is to take epsilon equals 0 in the system and then to solve it. Unfortunately, doing so yields a structurally singular system in which velocities and torques don't interact. What's the problem here? Since state variables are always finite and epsilon is infinitesimal, the two torques must be infinitely large, reflecting that they are impulsive. Hence, setting epsilon equals 0 in the system was improper. We actually proved in previous work that setting epsilon equals 0 in a system is okay, if and only if doing so does not make it singular. To overcome this problem, we propose three solutions. They all yield a restart solution that captures the preservation of angular momentum, a physical invariant. I insist that we use physics-agnostic reasoning only. The first solution consists in eliminating the two torques from the system since they are the impulsive variables. This is stated in step 1 and it results in the equation shown. Now we can safely set epsilon equals 0 since regularity is preserved. This is shown in step 2. And we finally get the wanted value for omega plus the value for restart. This works since torques enter linearly in the system. It cannot be done in general. A brute force alternative consists in taking epsilon equal delta, a positive non-infinitesimal small time step, and to solve the system for the next velocities and torques. We proved in previous work that this scheme is converging. This means that the so-computed values for non-impulsive variables converge to true values when delta tends to 0. The values of impulsive variables go to infinity. However, we are not interested in them and they can be simply discarded. We experimented this scheme in several small examples with success. Of course, we expect difficulties from the ill conditioning that follows from the nearly singular nature of the system. A natural improvement consists in rescaling the impulsive variables. Here, we know that the product epsilon times tau should be finite. So, we change the variable by rescaling the torques in the system as shown. This has the advantage of improving the ill conditioning of the brute force scheme. This advantage was confirmed by the experiments on small examples we did. A restriction is that this rescaling requires that the impulse order of tau is finite. Here, tau has magnitude order of 1 over epsilon, which by definition yields the value 1 for the impulse order. Unfortunately, impulse order can be infinite, for example if we use exponentials in the expressions. The question is how to make all of this systematic. In the next slides, we will show that computerized rule can mechanize the impulse analysis. All of this reasoning uses discrete time Euler scheme for DAE with infinitesimal time step. We need to analyze systems of algebraic equations where constants and functions are all standard, real, and epsilon is the only source of infinitesimal. The example we have seen is the system determining the restart of the clutch at an engagement. Say that the impulse order of x is alpha if and only if x times epsilon to the alpha is finite and non-zero. We don't comment this slide in detail, see the paper for this. On top, we show the syntax of a mini-language of algebraic equations involving constants, variables, and numerical expressions. It also involves the spatial infinitesimal number epsilon as only source of infinitesimal or infinite values. Then we show rules that transform such a system into a system of constraints, determining the impulse order of each dependent variable. To conclude, in our second talk, we have proposed a compile-time structural analysis that is really multimode. This means that a different set of latent equations is synthesized for each different mode. This is implemented by our tool DAE that is available for open experimentations. In our first talk, we completed this by a definition of structural analysis at mode changes. Our approach encompasses all systems exhibiting finite cascades of mode change events. In its future extensions, DAE will include this. In this talk, we have complemented this by proposing a systematic compile-time impulse analysis. Impulsive variables at mode changes can be identified prior to generating simulation code. This allows improving code generation. So far, it's a proof of concept contribution with no tool development planned soon. Tool development will depend on the expressed interest of users and on priorities in our team. With this, I conclude, and I am ready for questions if you have some.